Bonjour, welcome to the second video, 2-5 in the Essentials of Calculus. This video is going to talk about non-differentiability, and we're going to talk, now that we know what the derivative is, how to calculate it, some quick tricks to calculate it. We're going to talk about when can we not take a derivative? When can you not do it? So let's go ahead, let's look at the idea here. So it says non-differentiability, if my computer will respond. Okay, there we go. Okay, and that is when a derivative does not exist, right? That makes sense, not differentiable. Okay, and here we have some visual examples, and all of these are not differentiable at the x value 1. So just visually, you can see where these are not differentiable. And my computer is being very slow right now, so bear with me, I'm sorry. Okay, so right here, not differentiable. And right here, not differentiable. And right here, here, and here, okay? So let's talk about these characteristics that destroy differentiability. And they say the 5 characteristics are, well, the first 3 are grouped into discontinuity. So if you have a function that's not that's not continuous, right? It's discontinuous, then you do not have differentiability at that location. Okay, so what are they? You have holes, okay? You have jumps, you have vertical asymptotes, right? So these first 3 here, if it's not continuous, it's not differentiable at that x value, okay, at that x value. That's very, very important. Okay, the other 2 locations are sharp turns, and then if you have a vertical tangent line. And I kind of want to talk about this, right? So like, how do I know if I have non-differentiability? Well, for a hole, right, these are going to pop up in rational functions. Okay, so, and that's something like 1 over x. That's when, or sorry, this is not true. Let's go, they do pop up in rationals, but something like this, x over x squared, right? This would produce a hole at x equals 0, okay? So, that's not gonna be differentiable at that location. Also the same rationals, right, with the vertical asymptotes, okay? So if I had something like 1 over x, right, you have a vertical asymptote at 0. Well, I guess to match this, right, let's do this, 1 over x minus 1. Okay, that's exactly what you're looking at. So you have a vertical asymptote there, okay, not continuous. We know for jump discontinuities, this happens when we have our piecewise functions, and right, our 2 pieces, our cut point, they're not continuous, okay? So that's what produces there. For the other 2, the sharp turns, this can happen with piecewise functions also, but mainly kind of like what you're looking at here is absolute value functions. Absolute value functions, they tend to have sharp turn discontinuities. And then with vertical tangent lines here, this is when you get undefined values for your derivative. So if f prime of x has discontinuities, okay, so if I take a derivative and there's a rational function and I can't have a value, right, that makes the denominator 0, then you're not going to have differentiability. Okay, so that's just some of the things to pay attention to. So it says, note here, if a function is not continuous, it is not differentiable, right? So this is 1 through 3 here. Okay, that's what that first sentence says. A function may be continuous and still not be differentiable. Okay, so that's the last 2. So the last 2 here, these are continuous, okay, but we do not have differentiability at x equals 1. So let's look at these examples. Here it says, find the x values where f of x is not differentiable, and give a reason for each one. Okay, Number 8, this is the absolute value of x, and I hope you already have an idea of this, right? Absolute value of x, well, from 0 on, right, I have a vertical function, something like that, and then it's the absolute value, so all negative values become positive, and we have this. Okay, well, what's the point of non-differentiability? Well, that's going to be right here. That is at x equals 0, right? Because of a sharp term. So I can say not differentiable at x equals 0, and then the reasoning is because of a sharp turn. Okay, so there's that one, sharp turn. Number 9, piecewise. So I hope with piecewise you're thinking jump discontinuity, right? Because jumps are very common with piecewise. So that's the first thing that I'm going to investigate in this example, right? So I'll draw a little picture, and then at x is less than or equal to 0, I plug this in, right? And I get 0, okay, and I know to the left it looks like a parabola. And for the piece to the right, if I plug this in, okay, I get 0, but it's a vertical line, so it looks something like this. Okay, so clearly this is not jump discontinuity. I have a continuous function, but again, I mean, what's the issue here? Well, the issue is right here. Okay, so again, this is not differentiable at x equals 0 because of a sharp turn. And something else I kind of want to elaborate on is, what if I take f prime of x? So I'm going to take the derivative of each of these values, and for my first function we get 2x for x is less than or equal to 0, and for this one, for the second piece, I get 1 for x is greater than 0. And if we evaluate this, right, if I plug in 0 into the derivative for the first piece at our cut point, okay, I get an output of 2, okay, here. Now if I plug in 0 here, I get 1. So do you see how there's that jump discontinuity in our derivative? Okay, so if I'm looking at the derivative of our function, of our piecewise, and there's not continuity there, right, then that makes it non-differentiable, okay? So you have a jump discontinuity for the derivative, which makes sharp turns not differentiable, okay? So that's kind of what's going on there. Number 10. On number 10, we'll do the same thing. We'll do the same thing we just did here. We're just going to check for continuity. Piecewise, I mean, that's what I would say always do first. So I plug in my function, I plug in 0, and I get an output of 0. Here I plug in this cut point and I get 1. Okay, so what you have here is a jump discontinuity, right? So this is not differentiable at x equals 0 because of jump discontinuity. This is a jump discontinuity. Okay, so I mean that's what's going on, right? This is not continuous. All right, number 11. On number 11, I hope you immediately see a fraction and you say, hey, this is a rational, right? This is a rational function. And rational functions, you got to watch out for 2 types of discontinuities. You got to watch out for holes. You got to watch out for vertical asymptotes, right? Okay, so I'm going to go ahead. I'm going to reduce an x top and bottom to reduce my function to be 1 over x minus 1. Okay, so what does that mean? Well, this means that we have a hole, okay, at x equals 0. All right, and then also too, if we investigate down here, hey, I have an h value in the denominator, okay, so that means I have a vertical asymptote at x equals 1. Okay, so if I have a hole in a vertical asymptote, then hey, there's 2 pieces of discontinuities, so that makes it non-differentiable. Okay, so we can say not differentiable at x equals 0. Whoa, wow, what a hole. And at x equals 1, and this is a vertical asymptote. Okay, easy enough. All right, number 12. Number 12, what you have here is a cubic root function. I hope you're familiar with a cubic root function. It looks something like this. Oh, that's kind of bad. I'm supposed to cross through in here. We'll make it wider. Yay, now it looks good. Okay, and what you have going on here, this is going to be the last of our cases where you have a vertical tangent line. Okay, so this is continuous everywhere. We're in business. I don't have any sharp turns, but what I do have is I have a vertical tangent line. You're like, Schwarberg, how do I know that? Well, I can say, look right here, right through my terrible drawing. If I took the tangent line right here, you could see that you have a vertical tangent line. You're like, Schwarberg, your drawings suck. And I'm like, I know, I tried my best. Okay, so what I'm going to tell you to do here, right, if you suspect it, right, and again, I'll go back up to here. Here's a better drawing of it right here. Okay, so if you suspect it, again, take the derivative of that function. So I'm going to go ahead, I'm going to take the derivative of f prime. Okay, so f of x is equal to x to the power of 1/3. I would hope you would agree. And then we're going to take the derivative, f prime of x. Okay, so this is 1/3 x to the power of negative 2/3. Okay, and I'll just rewrite this. This is 1 over 3 times the cubic root of x squared. Okay, and you're saying, okay, so what's the big deal? Well, I'm going to ask you again, okay, so what's restricted domains? And I hope you would agree that right here, what happens if I plug in 0? Oh, my denominator is 0. Oh, the world explodes. Yeah, okay. So what you have here, right, is this is not differentiable at x equals 0 because of a vertical tangent line. Okay, so like this is the derivative, right? So the derivative would have an asymptote right there, right? Derivatives have an asymptote. Okay, so there you have it. These are what make functions non-differentiable. I cannot take the derivative, and remember, a derivative, all it is the slope of the tangent line. So okay, I'm taking just a point and I go off of it. That's the tangent line. That's the derivative. Derivative, slope of the tangent line. Okay, same thing. All right, hope you like this video. I have one more video on average rate of change, which is a crazy topic I know you've never heard of. Watch the last video. We'll talk about average rate of change. All right, catch you next time. Peace.